Okay, hi, welcome. So I got an email to answer a couple questions from the homework, and yeah, I have no paper, but I have crayons, and I have a Rescue Writer's coloring book, and so yeah, let's jump into this. Hey, can I use this? Okay, so one of the questions involves a good amount of no, what? Let me get. So one of the questions involves a trigonometric substitution, which comes straight out of Calculus 2. Now, if you don't remember how to do that, there's basically we're trying to leverage. Hey, yeah, it's okay. No, but that's what I'm using to teach. Okay, well maybe we can transition to a Pokemon coloring book. Let's do this one. Okay. Okay, so what do we got? Trigonometric substitution. So basically it leverages the Pythagorean identities, right? So we know we have, say, sine of t squared plus cosine squared of t is equal to 1, right? So that's what we got to start with. And yeah, I know, it's awesome, isn't it? So what we can do is it gives us one thing we're looking for. So 1 minus, say, sine squared of t is equal to cosine squared of t. And so what we want to do is we want to leverage this idea, the second line here, in order to, yeah, I know, it is cool, in order to do some integration theory. So what we're going to be looking for is things like this, where it's going to be, say, 1 minus y squared, 1 minus y squared inside of our integrals. And then we're going to choose y is equal to sine, and then we can, once we make that substitution, then we can go and change it to cosine. Now we could have some extra coefficients here, like if we had an a on the y, if we had ay squared, then we choose, then we choose something else. We choose square root of a y is equal to sine of t. And then we can still do the same sort of thing. And if we have a coefficient here, it's, again, we can finagle it. We just factor this one out, and to get a 1 here, then we'd have a coefficient on the y. And so that's what we do. There's another formula we can use, and we start with this 1 is equal to sine squared plus cosine squared, but then we divide both sides by cosine squared. You want to show them, buddy?
No.
Yeah, okay. Here, you can hold yours up. You can show them like this. All right. So you want to get started? No. Oh, camera shy. Okay. All right. We'll go back to this side. Okay. So what do we have for the other one? So here we have say 1 is equal to sine squared t plus cosine squared t, and that's the equation we start with. And now if I divide both sides by cosine, what do we get? Well, we get see, on the left-hand side, we get 1 over cosine squared of t is equal to tangent squared of t plus 1. Oh, I need that. Okay.
Hey.
Well, good thing we have yet another coloring book somewhere. Can I continue? No, that's yours. Okay. All right. I'll be right back. Okay. So. Ultimately, what that gives us is it gives us secant squared of t is equal to 1 plus tangent squared of t, right? And so that we would have this. And so what we're going to aim to do here is we're going to look for something like 1 plus y squared. And when we have 1 plus y squared, we want to make substitution tangent of t in for y, and then we can change that into a secant squared. And this will allow us to get to sort of collapse a lot of things and gets us out of square roots. So basically you'd have, like, say, the square root of 1 plus y squared, and then you make substitution with tangent, and then that turns into secant squared of t, and then you can take square root and you just have secant of t. That's the sort of thing that you're looking for. But also don't forget when you make this substitution, so if you say y is equal to, say, tangent of t, then you're also going to get dy is equal to, say, secant squared of t, right? Because we know the derivative of tangent is equal to secant squared. And same thing when we make substitution for y is equal to sine of t, you'd end up getting dy is equal to cosine of t, say, times dt. Okay, so another thing, see, let's find a nice page in this Pokemon coloring book. Okay. So we'll color over Caterpie. Oh, no. No?
It's my book.
Okay. Okay. Do you guys have a book I can borrow? Can I borrow
Please go to the book. To the book. Tell me the book.
Okay.
This one.
No, I can't use that.
To the
Can I
book.
use this coloring book?
This complete book.
I'll color on this one. Is that okay? Okay, so we're back to this one. Yeah, are you explaining it to them? Yeah?
This book.
Yeah?
To the book.
Okay.
This complete book.
Yeah, that's a Caterpie.
This complete
Yeah. Okay. So then another one of the problems involves partial fraction decomposition. And so there's the general goal is to split a fraction into a sum of fractions that you can then take an integral of easily. Yeah. So for instance, you might be left with say 1 over s squared minus 1. But then we know that is equal to 1 over s plus 1 times s minus 1. And so then the idea is you want to expand this in some way. This is a really easy case, but we have turn this into a over s plus 1 plus b over s minus 1. And then when you do that, you now have an equation where you can solve for a and b. You multiply both sides by, say, s squared minus 1, and then you have a polynomial on both sides. You can, say, compare coefficients, or other methods you can use. You can set s is equal to -1 and s is equal to +1, and then terms will disappear and you can solve for those. I think in this case, a is, say, -1 and b is 1, or maybe the other way around. But yeah, and so it could get slightly more difficult. So say, for instance, you have 1 over, say, s plus 1 squared times s minus 1. Yeah? Are we telling them? Yeah, okay. Okay, that's your book. Okay, okay. Yes, you go tell them. So, we could have 1 over, say, s plus 1 squared times s minus 1. And then this will give us, say, a over s plus 1. So you have one term for the s plus 1 squared. And then you could also have plus b over s minus 1. But then if you think about adding these two together and finding a common denominator, the common denominator wouldn't have s plus 1 squared. So if you want to make sure, yes? So you need to add a c over s plus 1 squared, and then when you add them together, you'd have the right denominator, and now you just need to solve for a, b, and c, sort of the same way you would have before. Then there's one other method, one other case that you need to worry about, and let's do it this way, and that's when you have an irreducible form, say s squared plus 1. Yep, okay. So let's say you have 1 over, say, s squared plus 1 times s minus 1. Then your irreducible term, you're just going to actually contribute two variables. So you're going to have a s plus b over s squared plus 1. And then we have plus c over s minus 1. All right, and so you're going to have a linear term over your irreducible. Okay, so I think it'd be way too much to actually try to solve the problems that I was asked about right here with crayons and coloring books and children who are very serious about maintaining ownership over their coloring books. Although they're doing their best. But yeah, so I think from this point on, I'll switch to. Yeah, yes, you're quite a cutie. All right. Can you guys say bye bye? Bye bye. Okay, we're gonna cut to my iPad. Okay, so I have my baby set up with snacks, watching Despicable Me. Minion scenes are on, so seems like they're pretty entertained. So we can go ahead and do this. All right, so we're looking at section 2.2, and just gonna do number 13 and 14 because I don't have more time. But these look like they might be some rather more tricky ones. Ones that really go back to the things you need from Calc 2. So the first one, number 13, gives us dy dx is equal to 3x squared times 1 plus y squared to 3 over 2. All right, and so this is number 13. Okay, so this is in the form where we have, say, p of x times g of y. So this would be our g of y, and this would be our p of x. And so then what we're going to do is we're going to divide by the y function and multiply both sides by dx. So we get dy divided by 1 plus y squared to raised to 3 halves is equal to 3x squared dx. All right, now what we need to do is we need to integrate both sides. So in order to find y, we would integrate both sides like this. However, while the right-hand side is trivial, this is just going to give us x cubed plus c, this one is going to take a little bit more work. So let's take a look at the second, or rather the left-hand side, and see what it gives us. So if we take a look, we're trying to find the general antiderivative of dy divided by 1 plus y squared to 3 over 2. And now the significant thing to notice is that 1 plus y squared is in here. Now if this, what our goal is we would like to change this from being a 1 plus y squared to something squared. And the way to do that is use trigonometry. So like I said before, we have two different things we're going to be looking for. If we have 1 minus y squared, that would tell us to set y is equal to sine of t. If we have, say, 1 plus y squared, that tells us to set y is equal to tangent of t. If I had an a here, in particular, more generally, if I have, say, a 1 minus a y squared and I have a 1 plus a y squared, then on the other side here, what we'd have is we'd just put, say, square root of a and square root of a. Okay, so since we're going with this case, that tells me then that dy is equal to a is 1, keep that in mind, so it becomes secant squared of t dt. Okay, so making those substitutions, we have dy and we have what we know what we want our y to be. So this gives us the integral of, say, secant squared of t dt divided by 1 plus tangent squared of t to 3 over 2. All right, now 1 plus tangent squared, the whole reason why we do this is because it satisfies the Pythagorean identity. And so on the top here, we still have secant squared t dt, but on the bottom now, 1 plus tangent squared of t turns into secant squared of t raised to 3 over 2. Okay, so now that bottom one, we take square root of secant squared, we get secant, and then we get, say, secant squared of t dt divided by secant cubed of t dt. And a little bit more work, we're going to get 1 over secant of t dt, and then this is actually integral of cosine of t dt. Okay, not too bad. All right, now we know that is equal to sine of t. Okay, pretty good, but now we need to be able to get out of sine, out of t, and we'd like to get back to y. So what we're going to do is we're going to go ahead and notice that we set y is equal to tangent of t. Well, y over 1 is equal to tangent of t, and if we think of this as being opposite over adjacent, then what we're looking at here is we have some angle, t, and then we have y, 1, and then we have, and so then we'll have y on 1, and then that would give us 1 square root of 1 plus y squared. So now if I want to take sine of t, it's going to be opposite of hypotenuse, right? So it's going to be y over square root of 1 plus y squared. Okay, so now we have the left-hand side figured out. That is this. So what we can do is we can go back over to this side. We get y over square root of 1 plus y squared is equal to x cubed plus c. And honestly, I think I'm just going to leave it like that. And that is an implicit solution to a differential equation. Now, barring any sort of mistakes or anything else in here, I think I did everything right. That's how you do it. Okay, let's take a look at number 14. Oops, I don't know why I keep writing 17. 14. Okay, taking a look at number 14, what do we get? So we have
dx dt minus x cubed is equal to x. Okay, so this isn't in the form that we would call separable yet. So let's do a little bit more work. And so I want to isolate the derivative. So dx dt is equal to x plus x cubed. Now this might not be obvious yet that this is two functions multiplied by each other, but we can think of this as being a function of x times of a constant function with respect to t. So now I can take this dx divided by x plus x cubed, and this is equal to dt. Integrate both sides. All right, so the right-hand side, straightforward, it just becomes t plus c. And on the left-hand side, we want to figure this out. So let's take this over here. We have dx over x times 1 plus x squared. Okay, so now this is an irreducible form. And so this is this is an irreducible term that we have in the denominator, and so that's going to tell us the sort of thing we need to do for partial fraction decomposition. So let's down here, let's just do partial fraction decomposition, x times 1 plus x squared. And so it's going to give me a over x plus bx plus c over 1 plus x squared. All right, now we need to figure out what a, b, and c are. Multiply both sides by the denominator, and so we get 1 is equal to a times 1 plus x squared plus bx plus c times x. And if I set x is equal to 0, what does that give me? Well, that gives me, let's see, you're going to get 1 is equal to a times 1, and then that next term is just going to go away. So we have a. If I were to set, let's find some other number that would be nice and convenient. Oh well, doesn't look like there is one, but let's just try x equals 1. We're going to have to do some solving here. So I have 1 is equal to, we know a is 1, so I'm just going to put that in there. So 1 plus x squared, so 1 squared, plus b plus c. So that is 1 answer. And what does that give me? Well, it gives me 1 minus 2, so it gives me negative 1 is equal to b plus c. Now let me put in x equals negative 1, and let's see what we get there. So I get 1 is equal to, a is 1 again, so I'm going to put that in there, and so it's 1 plus negative 1 squared, plus, now we're going to have a negative 1 out of that x here, so I'm just going to put minus 1 there. Then I'm going to get c minus b. All right, so that's going to give us, altogether, if I take this guy, which is 2, I move it over, that gives me negative 1 again, but then I multiply that by 1, so I get 1 is equal to b, say c minus b. All right, so we can figure out b and c pretty quick. We go ahead and add both of these equations. And so if I add these equations together, what do I get? So I end up getting 2c is equal to 0. And if I, say, take the difference of the bottom from the top, so I get minus 2 is equal to 2b, and so that tells us that b is equal to negative 1. Okay, assuming I did everything right, then what do we get? We get the integral of, let's see, we have 1 over x, and then we have minus x over 1 plus x squared dx. Okay, so first of all, the first term is easy. That's natural log of the absolute value of x, so we'll leave that in there. Minus the integral of x over 1 plus x squared dx. Now this is again going to be a u substitution, so we're going to have u is equal to 1 plus x squared, and that gives me du is equal to 2x dx. And so then that tells me then that this is natural log of ln of x minus the integral of, let's see, we almost have everything, but we're missing a 2, so if I, so this ends up being 1/2 of du over u, and so then we have natural log of the absolute value of x minus 1/2 as natural log of the absolute value of u, and the absolute value of u is 1 plus x squared, which is always positive, so I'll just put 1 plus x squared. Right, so then what do we get putting everything together? That tells us, let's put it in purple. So what do we get? On left-hand side, we get natural log of the absolute value of x minus 1/2 of natural log of 1 plus x squared is equal to t plus c. And yeah, that's the solution. Again, there's no solving for x here. X is a function of t, by the way. But this is an implicit solution again. Okay, cool. So those are those two problems, and hopefully this clears up things for a lot of people. I imagine trig substitution and partial fraction decomposition might have fallen out of your head since you took calculus 2, especially if you had calc 3 in the middle. So hopefully this is a good reminder. Yeah, in any case, I think my children are starting to get antsy, locked away in their high chairs with their snacks, and so I'm gonna go release them. Okay, thanks for listening.
Okay, so welcome back. I hope that helped. In any case, yeah, this is sort of my normal day-to-day, and except for a couple days a week, more or less trying to do everything while watching children. That's the quarantine for us. And yeah, so yeah, hey, I hope to help. And now I think I'm gonna go. All right, bye.
Bye-bye.
Bye-bye. Bye-bye.
Bye-bye.
Bye-bye.